Welcome to Lesson 8. So we're going to talk about non-parametric tests this week, and we're going to start with the Wilcoxon-Rank sum test. So we're going to review a little bit about our T procedures and then introduce this test for when we can't meet the conditions for a T test. So reviewing, remember, T tests are usually quite robust. That means that even if we don't meet all the conditions perfectly, the procedures tend to do pretty well. This is especially true if we have really big sample sizes. But if they're small, they're not going to perform as well when we have really out there outliers or extreme skewness. We're going to want to have a bigger sample size. So there are going to be some scenarios like if we don't have a big sample size and we do have very skewed data, that's going to be a problem. So really two small samples is one scenario, and then have extreme skewness or extreme outliers, something that's going to really mess with the mean. In that case, it's not going to be good to use a t-test. So when we want to talk about the mean, we are using normality assumptions if we're using t procedures. So if we want to do a t-test, so like a one sample z-test for a mean, or one sample t-test, a two sample t-test, they all rely on the distribution of the sample mean is normal. So that sampling distribution of x bar is normally distributed. So there are a couple of ways we can know this. If we know the population's normally distributed, then we're good. The sampling distribution of x bar will also be normally distributed. The other method we've been using is that central limit theorem. Hey, if our sample size is big enough, we know the central limit theorem is going to kick in, and that's going to make it so that the sampling distribution of x bar is normally distributed. However, in the real world, we may not always have this scenario. So if we know, like if we are looking at the data that we have and it's clearly not normally distributed, and we have small sample sizes, there are other tests that we can use. So you're not going to want to use a t-test if you know that these conditions are very much violated. You do not want to use them. You're going to get inaccurate results. You don't want to run a t-test and then talk about the t-test results when you shouldn't have run a t-test in the first place. Okay, so when we know that our data aren't normally distributed, that central limit theorem is not going to kick in, so we shouldn't use z-methods or t-methods. We can use non-parametric tests. So non-parametric just really means that we aren't assuming that it follows a normal distribution. So absolutely, that's the big thing. We're not assuming that the sampling distribution of x bar is normally distributed. And the two that we're going to look at here, we're going to look at the Wilcoxon sign-rank test and the Wilcoxon-rank sum test. So here, when we have a one sample setting, so we have maybe one quantitative variable that we're looking at from one population, we would look at a one sample t-test. If we had a matched pairs scenario, we would look at a matched pairs t-test. So then the non-parametric version of those tests is that Wilcoxon sign-rank test. And then if we were to look at two independent samples, so we wanted to compare, population 1 to population 2, and we're looking at probably means, but something quantitative for sure, we would use a two-sample t-test if we meet the conditions. But if we don't, we could use the Wilcoxon-rank sum test. So rank sum and signed rank. So what these tests do is they transform our raw data into ranks. They go ahead and they sort the data, and we rank them from smallest to largest, or if you're looking at differences, smallest to largest usually. So rank tests, they concern the center. So if we were using normal distributions, so t methods or z methods, we would be looking at the mean. This means that our question of interest, our parameter of interest, our hypotheses, they should all have the mean in them somewhere. However, if we are dealing with a scenario where we don't have a normally distributed statistic, we're going to look at non-parametric tests, and we're going to look at the median. So in general, if our sampling distribution is nice and symmetric, you look at the mean. When it's not nice and symmetric, the median is a better measure of center. If you think about it, it's like if I have a couple of really, really high outliers, they're going to pull the mean towards them, but they aren't going to impact the median. So that's why we would go for the median if we had skewness or outliers. So raking the data, it's essential to helping find that median. But one of the big things you have to do is you have to put all of the values in order. You have to sort them from smallest to largest. So ranking. So here's a really small case scenario. There's 7 in this data set. So our first step is going to arrange them in order from smallest to largest. So just looking here, I find it helpful to go, 15 is the smallest, I'll cross 15 off. Then write 15, and then write 16. And that way I can keep track of any doubles for sure. So I can go 15, 16, 18, looks like 19's next, 22, but I've got 2 of them, so 22, 24. So now I've put them in order. And you can then move to rank them, like this one would be 1, this one would be 2, 3, 4. So here it's a little goofy, right? Because it would go 5, 6, but 22 is the same number. So instead of 5 and 6, it's the average of 5 and 6. So 5.5, 5.5. If you add them together, it's 11. So 5 plus 6. And this would be 7. So that's how we deal with ties. So here we had 2 values of 22. And that means that we take their ranks 5 and 6 and we average them. So 5.5 and 5.5. So there's our ties there. So be wary of ranking. This is something you only want to do if you absolutely cannot use T methods or Z methods, because you lose a lot of information by only using the ranking. You lose the actual values, that information. So it's pretty much like, was this an increase, was it a decrease, versus by how much. So it absolutely is a big deal to reduce your information to just the ranks. So absolutely, if you move from your original observations, those original values, to just their ranks, you don't have as much information about what was going on anymore. So absolutely, one thing to note here is our question of interest has to change. Our parameter of interest is different now. Our hypotheses have to be different, right? Because we just are not looking at the mean anymore, and we are not asking the same questions we were asking before. So the Wilcoxon rank sum test, hypotheses. So here it's interesting because these hypotheses are going to be about distributions. So the null is just going to say, the distribution of population 1 is the same as the distribution of population 2. And the alternative is saying, no, the distributions are not the same. It could be that one in particular is systematically larger. So that would be saying like, we think, the heights of one of the two universities, U of O or OSU, is systematically taller than the other, something like that. So these hypotheses are non-parametric. They don't have parameters in them. So note, you might see in where they are written about the median, but there are like a little bit of an extra condition there if you want to write it about the median. So these are just simply written about the distribution in general. And note, this example right here does not include the context, so you should include context about the problem in your hypotheses as well. So Wilcoxon-Rank sum test. So interpreting the null hypothesis. So if your sample sizes are the same versus not, the idea is if the two distributions are the same, that means they have roughly the same number of small observations, the same number of medium, the same number of high, like roughly the same, then the distributions overall are going to be roughly the same. So the sum of the ranks are going to be roughly the same for that. Versus if they are different, so if we're looking at two groups here, if they're different, then the sample sizes, you're not going to have exactly the same number of well ones, the same number of medium, and the same, or even approximately necessarily. It's more proportionally, oh, I have, half of mine in sample 1 are low, and roughly half in sample 2 are low. Roughly a third in sample 1 are medium, roughly a third in sample 2 are medium, and so on. It's proportional. It's not the exact same number or even approximate number, because you might have wildly different sample sizes. So you just can't hold them to quite that same expectation. So the steps here for the Wilcoxon-Rank sum test. So absolutely, no matter what kind of test we're doing, we're going to want to have a random sample. So here it says simple random sample. It can be other types of random sample as well. So it doesn't have to exclusively be a simple random sample, but either way, we want a random sample. We want to know that the sample that we took represents the population that we're trying to make a statement about. So denote our sample sizes. So if we have two sample sizes here, and 1 is going to be the sample size for sample 1, and 2 is going to be the sample size for sample 2. And so then we're going to want to state our null and alternative hypotheses. So we want to say, the distribution of this group and this group, and you need to define what those are in context, are, approximately equal. And then our alternative will say, hey, no, we think either one in particular is systematically higher, or we just think one of them is systematically higher. So calculate the Wilcoxon-Rank sum test statistic. We will go through that step. So first, we're going to calculate capital N. So basically, capital N is combined sample size. So just your total sample size if you combine both samples. Then we want you to rank all of them. So put all of them in order from smallest to largest, regardless of which group they're in. Then you're going to calculate the sum of the ranks for each sample. So you're going to still keep track of which sample each observation's in, but if an observation from sample 1 has the smallest value, it's going to get a rank of 1. If an observation from sample 2 has the second smallest, it gets a rank of 2, and you're going to just count up the ranks for each sample. And we will end up using, so whichever group has the smallest number of ranks, so once you add them up, we will go ahead and use that group to calculate the Wilcoxon-Rank sum test statistic, which is W. So then once we get that, we can use a z-table to calculate a p-value. Basically, we will calculate an approximate z-test statistic. There will be an equation that we plug our values into. Then we'll have a z-test statistic, use that z-table, get a p-value. And then this is that final, like, now that you've actually gotten your test statistic, you've gotten a p-value, now you have to go back and actually answer the question. So write your two-part write-up, like, hey, we reject or fail to reject the null with a p-value of blank, and then tell us, oh, there is blank evidence that, and you have to say the alternative in context. So that normal approximation of W, there are a few steps involved here. So this capital W is going to be, once you count up the ranks for both groups, whichever group has the smallest ranks is going to be your W. That minus 0.5 minus mu W, which is something else that you have to calculate, over sigma W. So mu W, you're going to calculate, so whatever sample goes with this W, that sample size times capital N plus 1 over 2. And then sigma W, it's all under the square root, N1 times N2 times capital N plus 1 over 12. Once you get that, you have a z-test statistic. And you can either use a calculator to get a p-value, or you can use a z-table. So once again, yeah, make sure that N1 here, that's going to be whatever sample size goes with the group that has the smaller rank. Okay, so here is the example that we're going to go through for this lesson. We have recorded calories from two different sports drink companies. So we have drink company A and drink company B. They went ahead and they grabbed 4 from each company and recorded the 4 drinks from each company and recorded the number of calories in each drink. And so we want to know if there's evidence that one company has systematically lower calories than the other for the same 8-ounce serving. So if they're all serving 8 ounces, is one of the companies, having lower calories than the other in general. So our first step is going to state, like, hey, what is their question of interest? So are the calories systematically lower for one of the two drink companies, company A or company B? So there is no mention here of a mean because we aren't looking at means. With a sample size of 4 in each group, we really probably shouldn't be using T methods at all. That would not work out well here. And so since we're using non-parametric methods, we don't have a parameter. Non-parametric means no parameter. So that's what our non-parametric test is. So we don't have one in particular. Note, some tests will say, hey, you're comparing medians, but it does depend if you're comparing medians, that you can assume that the distributions are the same between the two groups, and that might be a difficult thing to assume. Okay, so same problem. Now we want to look at our hypotheses. So remember, it's non-parametric, so our hypotheses won't have parameters in them. However, they should still be talking about that general population, or the two general populations we're looking at, company A and company B. So by default, we're going to assume nothing weird is going on. There's no difference in distribution of calories between drink company A and drink company B. They are the same. What would be interesting is if we could find if one of them's different, right? So we could say, for our alternative, calories are systematically higher for one of the two drink companies. So once again, here we do not have a suspicion one way or the other. We don't think that company A has lower calories or company B does. Not ahead of time, we don't. And so then for significance level, there's not a whole lot of information in this. we're going to use 0.05. 0.05 is a good default. So if we give you a problem that requires any sort of test and we don't give you a significance level, it's usually okay to go ahead and just use 0.05 and feel welcome to clarify with us. Like, hey, I don't see this. Is 0.05 okay? Chances are we're going to tell you it's perfectly fine. So here we want to go ahead and order them. So we're going to take all 8 different calorie amounts for the 8 drinks that we have, put them in order. So the lowest is 80, then we have 100 and 110, 119, all the way up to 170. So now I'm just going to rank them. We have no ties. So rank 80. So calories, 80 calories is the lowest we saw. It gets a rank of 1. Rank 2 goes with 100 calories. And we kind of kept it color coded here, right? So these ones right here, those are associated with drink company A. Versus these ones, those are associated with drink company B. So if I want to say, hey, what are the rank sums for drink company A? I need to add those light blue boxes up. So there's drink company A. So that's 1 plus 2 plus 3 plus 6. Those are the ranks associated there. So I get 12. Versus if I want to look at the rank sums for company B, it's 4, 5, 7, and 8. Add those up, I get 24. So we're going to use W equal to 12 because this is the smaller of the 2 ranks. We don't want to use the 24. We want to use the 12. So that's what we should use. So what is my rank sum test statistic? So we're going to use W equals 12 because it's the smaller of those 2 ranks. So for simplicity, it is just easier. You could use the other, but it's easier to kind of goof up when it comes to the p-value. So we're just always going to take the smaller one. So finding the z approximation. So noting here, it was really, really nice because n1 was equal to 4 and n2 is equal to 4. Those are both really, really small sample sizes. Capital N, that's 4 plus 4, so that's 8. Right, that's the total sample size. So I already have, well, that end. W was equal to 12. I have everything I need for all of these steps now. So looking at mu W, so that the mean weight here, it's going to be 4 times 8 plus 1 over 2. I'm going to get 18. Then looking at calculating sigma W, plugging in 4 times 4 times 8 plus 1 over 12, square root that, end up getting approximately a 3.46. So now I have everything I need to plug in to step 3. So 12 was the smaller of the sum of ranks there, minus 0.5, minus that mu, that 18, divided by 3.46. I end up getting a z test statistic of negative 1.88. And in general, if you're looking at a z score, z test statistic, it makes sense to round it to 2 places past the decimal because that's pretty much, if you're using a z table, that's how many places the z table goes out to. So if my z test statistic is negative 1.88, we want this area here to the left, that shaded area. Negative 1.88, kind of just draw a line down there. So it's negative 1.8. That tells me which row. And 0.08. So the idea is if I were to recombine them, I would get negative 1.88. So this tells me which column. So my p-value, it's always going to be one-sided here. 0.0301. So always one-sided for this kind of test. So our p-value, 0.03, it's small. It's definitely smaller than our significance level. It's strong enough evidence, I would say, here to change our mind. So if you want to use the calculator, you can go to that stats and then go to z-test. You plug in stats there, so you tell it what you want for mu. That's that mu w. Sigma, that's sigma w. X bar should be that w minus 0.5. So 12 minus 0.5. And then always pick that lower than, because the way we have it set up, it's always going to be lower than. And then tell it to calculate, and look, our p-value, it matches what we got from the table. It goes out to more places, but we're totally happy if you go out, if your p-value is out to 4, it's good. So here, with a p-value of 0.0301 at the 0.05 significance level. So based off of that, I would say that's a p-value that's smaller than our significance level. We're going to reject the null hypothesis. So then looking at the spectrum here, I would say there's relatively strong evidence. So that drink company B has systematically lower calories than drink company A. So whichever one had the lower ranks is systematically lower than the one that had the higher ranks. That's how it works. So that's how we wrote it up here. So when to use this rank sum test? So the first step is if you are looking at a variable that is quantitative, you need to have two independent samples from two independent populations. So no matched samples, not for this test. It's going to be scenarios where your sample sizes are really small, or you know at least one of the populations is not normally distributed, and you know that the central limit theorem is not going to, kick in and save the day. You can use this for large sample sizes. However, if you have large sample sizes, a t-test is going to be a lot better than a rank sum test. A rank sum test is kind of like we're sorry you can't use the t-test, here's something you can use instead. Never use it instead of a t-test if you have large sample sizes. So what you want to test, the distributions of the two populations are the same versus no, they're not. One of them systematically higher or systematically lower than the other. You may see that some people might write, hey, the median 1 is equal to median 2. It does require that you believe that the shape of the two distributions are the same. Honestly, with a sample size of 4, it is really hard to tell if that's true. It's really hard. So it's easier and just probably more consistently better to just talk about the distribution of group 1 and the distribution of group 2. And in general, almost always, we're going to deal with the alternative is one-sided. At least in ST202, we're not going to throw you a curveball. They're going to be one-sided in our class. So that's it for Lesson 8. We'll see you for Lesson 9.